Today we'll start with the Cartesian coordinate system. In Cartesian coordinate system, we have x-axis, y-axis and z-axis. When x equal to 0, we call it yz plane. When y equal to 0, we call it zx plane. When z equal to 0, is called the xy plane. This xy plane is called the horizontal plane, and the zy or zx is called the vertical plane. In Cartesian coordinate systems, a volume is represented by a rectangular shape. You can check A, B, C, D, E, F, G. This is your Z axis, this is your Y axis, this is your X axis. Any point in the space in Cartesian coordinate systems P, X, Y, Z is measured in this fashion. First, drop a foot of the perpendicular to the xy plane or horizontal plane. Then, draw the perpendicular to the line x, draw the perpendicular to the line y, and measure the distance from the foot of the perpendicular P to the line y is your x, and draw the line from foot of the perpendicular to the line x. This distance is y, and the distance from the foot of the perpendicular to the point, this distance is called z. So any point in the space is measured in this fashion. In Cartesian coordinate systems, x varies from minus infinity to infinity, so three-dimensional. Y varies from minus infinity to infinite, and z varies from minus infinity to infinity. Infinitesimal small shape, that is differential elements. So a differential element is represented by a rectangular box. The differential length along y-axis we designate as the dy. Differential length along the y-axis we designate as the dx, and differential length along the z-axis we call it dz. So obviously, if I ask what is the volume of this differential, I can easily say that dx into dy into dz. And the differential displacement dl is a vector quantity, line vector. It is represented by dx, unit vector along the x, ax, dy, unit vector along the y, which is ay, dz, with unit vector along the z, which is az. Now question is how to find the differential surface. Differential surface in case of Cartesian coordinate systems, you can have 6 surfaces. I have told you in a closed surface, the unit vectors normal to surface is always perpendicular to the surface. For example, I want to find the surface vectors B, Q, R, C. This surface, differential surface, is the dx into dz, dx into dz. And what is the vector normal to the surface, outward to the surface? So it is ay, unit normal vector. Similarly, you can find ds. For example, I want to calculate the ds for this surface A, B, C, D. A, B, C, D. So what will be that? dz, dy, dz, dy, then ax along these directions. Similarly, I want to calculate the surface vectors for the top surface. So ds, a, p, q, b, a, P, Q, B. So I can write dy dx, dx, dy, and unit vector normal to the surface, outward to the surface is your AZ. So quite easily you take any surface and watch for the unit normal vectors, then surface area into that unit normal. So any vectors in Cartesian coordinate systems can be represented by Ax, that is the component of vectors along x-axis. So it will be represented by these unit vectors along x-axis, then component of the vectors along y-axis plus component of the vectors along z-axis, Az and small az. Next we will move to the cylindrical coordinate system. In the cylindrical coordinate systems, any point P is represented by rho, phi and z. What is the rho and phi and z? First of all, from the point P in the Cartesian coordinate systems, drop the foot of the perpendicular to the xy plane and join this point Q. This distance is your rho. Then what is the phi? Phi is measured from x-axis, and the angle between the OQ and OX and measured in the positive direction from the x-axis. That is your phi. And Z is as usual the distance between the P and Q. So now come to the unit vector. Unit vectors along the rho axis is called it a rho. How to find the unit vectors? Very simple. Keep rho constant. When you keep rho constant at this point, so and all other things are varying, you will have the phi will varies from 0 to 360 and z will varies from minus infinity infinity. So you will have a cylinder. So the unit vector will be outward to the surface. So outward to surface or perpendicular to the surface will be the unit vectors. For example, if it is a cylinder, the unit vectors a rho is the this. So this is the perpendicular to the rho constant. Same way, so keep the phi constant, rho varies. So plane of constant phi, you can see this plane. Okay. So when this plane, then this perpendicular to unit vector perpendicular to this plane will be the a phi unit vectors along the phi axis. And z usually you know when z is constant, this top plane you can see, and this is will be the unit vectors perpendicular to this plane will be the unit vectors along the z axis. So this will be the arrow, this will be the a phi, and this will be your a z, and they are mutually perpendicular. Mutually perpendicular, how to find out? Also these coordinate systems are right hand coordinate systems. That means when you place thumb, index finger and middle finger of your right hand perpendicular to each other, then it will definitely align with the rho, phi and z. Just keep thumb in the direction of your rho axis arrow. Your index finger will be in the direction of the phi and your middle finger will be in the direction of z. That's why it is called the right hand systems. In a right hand coordinate systems, a phi cross arrow cross a phi equal to AZ, and A phi cross AZ, okay, you will get the A rho, and AZ cross A rho, you will get the A phi. The rho varies from 0 to infinity, phi varies from 0 to 360, or we call it 2 pi, and Z as usual it varies from minus infinity to infinity. So any vectors, from the basics you have studied in your intermediate, that any vectors can be decomposed into the horizontal and the vertical component. This will be applied in the later on. We'll see when you have rho here, when you have phi, this component is the horizontal component, is called the rho cos phi, this rho, and cosine of this angle we got the rho cos phi. This length is your rho cos phi. This length is your rho sin phi. And also you know from the Pythagoras theorem, x square plus y square is equal to rho square. You check, same, rho square phi square, that is a rho square cos square phi plus rho square sin square phi, you know, equal to rho square into cos square phi plus sin square phi, which is rho square. Another thing I want to discuss, it is very important. If this is your 90 degree and this is also 90 degree, this angle theta is same as this angle theta. You can easily prove it. The YOP is the 90 minus theta, this angle, right? So this angle will be the 90 minus theta, which is theta, as I have marked. So whenever you see both the pairs perpendicular, this is perpendicular and this is perpendicular, this angle phi is equal to this angle. Now we are going to find unit vectors of cylindrical coordinate systems in terms of unit vectors in Cartesian coordinate systems, and unit vector of Cartesian coordinate system in terms of unit vectors of cylindrical coordinate system. Here I have shown, you should not have any difficulty. I am sticking to the conventions. My angle phi measured from the x-axis towards the y-axis. So you can easily say that this plane is your xy plane or horizontal plane. You can see in a three-dimensional notations like this. This is your x, this is your y, and this is your z. Clear? So I have depicted here x and y, and angle is measured from x-axis, which is your phi. We know that unit vectors along x and y and z are the ax, ay, az. And also we know that unit vectors along the rho phi z is the a rho, a phi, and az. A rho is the ax cos phi, plus from this side this is your ay, so ay sin phi. Similarly you can write a phi. So if this is your a phi, how can you write in terms of ax and ay? If it is your ax, what will be this? Minus ax. This will be the minus ax sin phi plus ay cos phi. Then az remains same. Az is az. So same way you can write for the reverse in terms of Cartesian coordinate systems unit vectors in terms of cylindrical coordinate systems. So ax is the a rho cos phi. If it is, this axis is a rho, so a rho cos phi, like this you write a rho cos phi, and a phi sin phi, but this is in the different directions, so minus a phi sin phi. Similarly ay a rho sin phi, this a rho sin phi, then a phi cos phi, and az remains az. Now suppose you have a vectors a, you want to convert these vectors into the cylindrical coordinate systems. Scalar component a rho vectors a dot unit vectors along the row axis. So a vector a, then a rho. Component of the vector along row axis. How to find the component of vector along the particular axis? Vectors, when you dot product with the unit vector along that axis, you will get. So you have write down the a x ay dot arrow. What is the arrow in terms of x and y? This is arrow x cos phi plus ay sin phi. Next, we need to find the a phi, component of the vectors along the phi axis. Similarly, write a phi, so minus ax sin phi, then plus ay cos phi, then az is simply az. Coordinate systems, so arrow, put the value arrow, then a phi plus az. What are the arrow here, put these values, then a phi, these values, this. In similar way, you also write, suppose you have been given vectors in the cylindrical coordinate systems like this, you want to convert into the Cartesian coordinate systems. You can find easily ax is the vectors a into ax, so vectors a is the arrow plus a phi plus az into dot of the ax in terms of rho phi z. Here is the a rho cos phi minus a phi sin phi. So a rho cos phi minus a phi sin phi. So from here you can find, similarly you will find the ay az, same az. So now you can write the vectors ax plus ay plus az. That's all. Now come to the differential element. So as you know that we are moving along the constant radius. You know from the basics of the trigonometry, if it is your theta, this arc length L equal to, if this is your radius, so L equal to r theta. You can see this is a cylinder, you have cut the cylinder here. So this is the arc length and it is a differential length. So this length is your rho d phi. And this length, you know, very simple, d rho, this one, dA is the d rho, and dz. Okay, so parallel to the rho axis, rho d phi, parallel to the rho axis is the d rho, and parallel to the z axis is the dz. Our differential displacement. And differential volume product of this, because infinitesimal small, I can multiply all. So rho, d rho, d phi, dz. Now important terms come the different differential area. Now check this differential area. That is ds, what is that? PABQ, which is, you see, rho d phi into dz. So rho d phi into dz, and the unit vector normal to the this surface outward, that is your arrow. And similarly ds vectors, let's say top, S D A P. So SDAP will be your rho d phi d rho az, because the unit normal vectors outward to the surface is the az direction. Similarly ds DABC, DABC. So you can say, it's very simple, it is the d rho dz, and unit vectors is your a phi, because out of that surface is the a phi directions. Next we'll move to the spherical coordinate systems. A little bit tougher to understand, but it is not difficult. So any point in space is represented by the r, theta and phi. So r, what is the represent? Any point here, the point P, or you can say point your P here. So same point P, that is the distance from origin to the point, that is length of the, use the shortest distance, length of, from the origin, okay, to the point is your r. Theta is the angle from the z axis to the r, and then phi, same way, when you draw a semicircle or quarter circle of radius r, okay, or you can say when you make this theta angle to 90 degree, this will meet at the xy plane and join this, and you know what is this? This is your rho now. So same way, angle phi is the same as we have defined for cylindrical coordinate system. See, we have seen that phi is measured from x-axis, theta is measured from the z-axis, and when you have a constant theta, you depict a cone. So unit vectors perpendicular to this plane is your a phi. You see, this is your a phi, and for a constant phi, you know, it's a plane, this plane, constant phi. So perpendicular unit vector will be perpendicular to this plane, so this will be a phi. For constant r, when you have a constant r, all others varying, so it is a sphere of constant radius. But because spherical coordinate systems, when you have r constant, all around moves, because all other things varying, so sphere, so out of these spheres will be the r. So r phi, r theta phi are mutually perpendicular. You can see r cross theta, ar cross a theta gives you the a phi, then a theta cross a phi gives you the ar, then a phi cross ar give you the a theta. Then you see the how I am decomposing. This is a point P, X, Y, Z. and this is your r. So this is your theta, and this is your r. So obviously this length will be the r cos theta, and this will be your r sin theta. This one, this length r sin theta. If it is your r sin theta and this is your phi, when you decompose this will be your, this is your r sin theta, let's say it is rho. So you know that this x component will be the rho cos phi. So rho cos phi. So this is your rho is your r sin theta cos phi. Similarly, this will be your rho sin phi. So r sin phi sin theta. And from x, y, z, how to find the r? R equal to x square plus y square plus z square root over. Theta equal to tan inverse is x square plus y square root over upon z. Then phi as usual, tan inverse y upon x, z equal to r cos theta. Then x equal to r sin theta cos phi and y equal to r sin theta sin phi. Here clearly everything depicted. Now differential elements. Little tricky to understand here. We have already seen one part here. This is your, what is this? We know this is my rho and this will be the rho d phi. But what is the rho? That is the questions. Rho we have seen, if it is your r and this is your theta, this is your r cos theta, this part, and this rho is equal to r sin theta. So this length is your rho d phi. Rho is your r sin theta. Okay, r sin theta, and d phi, see, r sin theta d phi, this length. This is very clear. This is your r and this is your d theta. So this arc length will be the r d theta, and this is dr. dv will be the multiplication of all r square sin theta dr d theta d phi, and differential length for r dr ar plus for theta r d theta a theta plus r sin theta d phi a phi. Now this surface area is quite important. Why? Because whenever you place an antenna here, it will radiate all around space. You need to find the, what is the power? You know the radiation density? Radiation density is the power per unit area. So all around, suppose I have 10 watt power, so it will be radiated all around this spherical surface. What is the area of the sphere? 4 pi r square. So power density becomes P upon 4 pi r square. Suppose somebody asks you though, what is the power received in this area? So obviously this power density and this area, differential area, then integrate for different values, that is theta and phi. So clearly you can see this area P Q, that is the surface of that sphere, P Q R S. So ds PQRS, very important. So multiplication of the both. So this is the r d theta, this is the r sin theta d phi. So r square sin theta d theta d phi normal vector will be perpendicular outward of the surface, simply AR. Same way you can look for the other surfaces and accordingly you can multiply and find the surface. Now we'll find the interrelationship between the unit vector in the Cartesian coordinate systems and unit vector in the spherical coordinate systems. Or first we'll find the unit vectors of Cartesian coordinate systems in terms of unit vectors of spherical coordinate systems. This is your z, this is your x axis, this is your y, and this is your rho. You can understand this in the spherical coordinate systems. So what happens here? I depict here z and rho. I depict this one for to represent very clearly theta and r. So this is your angle theta. So this will be the unit vectors. This is the r, and this is the unit vector a theta. Sorry, a theta, and this is unit vector AR, and this is your unit vectors A rho. I have represented the horizontal plane xy plane, and the phi is measured from the x axis phi. So this will be your A phi, and this will be your A rho. So I can write like this: AX is equal to A rho cos phi plus, see, I can write AX as the A rho cos phi, and this is my A phi. Okay. Just remember, I have told you this angle is 90, this angle also 90. So this is your phi. So this will be the phi. So this will be the plus minus of this A phi sin phi. So I got A rho cos phi minus A phi sin phi, as we have already seen in the cylindrical coordinate systems. Similarly, you can write AY. AY is your A rho sin phi, then plus A phi cos phi. But question is, what is the A rho? Here is the answer. Your A rho is your C. This is the AR. This here is the theta. So the A rho will be the AR sin theta. And just we know the basic. This is your 90 degree. This also 90 degree. This is theta. So this will be also theta. So you can get A theta cos theta. So A rho is the AR sin theta and A theta cos theta. So now AX becomes A rho. In place of A rho you put this. So AR sin theta cos phi plus A theta cos theta cos phi, then this one minus A phi sin phi. In a similar fashion, you can write AY is equal to AR sin theta sin phi plus A theta cos theta sin phi, then plus A phi cos phi. And what is the AZ? Can anyone say AZ? AZ Very simple. From here you see AZ will be the AR cos theta, and this is the A theta direction, this is your A theta direction, and this is your theta minus A theta sin theta. So AR cos theta minus A theta sin theta. This is the expression of unit vector in Cartesian coordinate system in terms of unit vectors in the cylindrical coordinate systems. Now we'll move to the reverse way. Unit vectors of spherical coordinate systems in terms of Cartesian coordinate systems. Now from here your AR you can easily write AR is equal to A rho sin theta plus AZ cos theta, and A theta, this is the A theta, so A theta is equal to, because this is the theta, then obviously this is your theta, so A rho cos theta, here is the minus AZ unit vectors, so minus AZ sin theta, and A phi is equal to, from here you can write A phi in terms of obviously xy, so this is the phi, so this will be the phi, so A phi will be the minus ax sin phi plus ay cos phi. But you know what is the A rho? A rho is here, from here A rho is your ax cos phi plus ay sin phi. Now put these two values here, so you can find A rho is the ax sin theta cos phi plus ay sin theta sin phi plus az cos theta. Similarly, A phi you can write A rho is the this, so put these values ax cos theta and cos phi plus ay cos theta sin phi minus az sin theta, and A phi we have already written. So this is the spherical coordinate systems unit vectors in terms of unit vectors of Cartesian coordinate systems. So now question arises, suppose any vectors has been given in the Cartesian coordinate systems, that if you want to convert into the cylindrical coordinate systems, so first you find AR is the A dot AR, A theta is equal to A dot A theta, A phi is equal to A phi. So you will be using all this AR, A theta and A phi for this here, and you will get the R component of the vectors, theta component of the vectors and phi component of vectors. Vectors has been given in spherical coordinate systems, and you have to convert into the Cartesian coordinate systems. So Ax is equal to vectors A into Ax, Ay equal to vector A dot Ay into means I meaning dot product, then Az A dot Az. So Az already we have expressed the x, y and z in terms of spherical coordinate systems before. Here you will be using these pairs to find the vectors in the Cartesian coordinate systems.